Soil is a non-renewable natural body that is fundamental to ecosystems and social well-being due to its multifunctionality. It is widely recognized as the foundation for food production, but it is also the habitat for a vast diversity of organisms, regulates the hydrological and biogeochemical cycles, and serves as a historical archive preserving the planet's geological and archaeological memory. However, a lack of care and poor soil management have resulted in the degradation of approximately 33% of soils worldwide and 75% in Latin America and the Caribbean. This means that the soil is being lost, and consequently, we are losing biodiversity and climate regulation capacity, while putting food, water, and energy security at risk. Due to its productive importance, soil faces enormous pressure. Agriculture, livestock, urbanization, and renewable energy production, among other human activities, demand vast expanses of land. In this context, agrivoltaic systems can be an alternative to reduce competition for soil by combining energy and agricultural production on the same surface. However, they can also lead to degradation if sustainable management is not ensured. Therefore, it is important to understand what happens to the soil in these systems, and, before establishing them, to conduct a detailed study of the soil characteristics at the site, its land use suitability, and its susceptibility to degradation. The installation of solar panels modifies the soil's microclimate. It changes the radiation reaching the surface, temperature, and humidity, as well as the way rainwater is distributed. These changes can be positive or negative, depending on the design, soil type, environmental conditions, and management. In some contexts, shading reduces thermal and water stress and helps conserve moisture. In others, it can affect biological activity or nutrient dynamics. Installing agrivoltaic systems on highly fertile soils can underutilize their agricultural potential. In contrast, in arid zones or already degraded soils, the shade from the panels can reduce evapotranspiration and promote moisture retention in the soil, leading to more efficient water use. Additionally, it can open opportunities for the recovery of eroded or low productivity lands. The installation of these systems must minimize soil disturbance. This involves planning access routes and machinery traffic, avoiding soil compaction, and controlling runoff to prevent erosion. The soil should not be treated as a passive surface, but as a living system that must be managed properly. Practices such as maintaining vegetation cover, promoting organic matter content, and protecting soil structure are essential to guarantee agricultural production. The stability of photovoltaic structures and the maintenance of the ecosystem services that the soil provides us. Thus, agrivoltaic systems can contribute to food and energy security, provided that in their design and implementation, the soil is considered as a fundamental component.